Hello everyone, my name is Bora Demir and today I'm going to explain you my electric and electronics digital design project, Integrating Calculator. Here you can see my codes. I designed my codes in a modular manner. This is the top module of our integration module, which contains all of the other modules and regulates the connections and relations between those. You can see the whole code over here. This is where you put inputs and the final outputs occur. Our first module is an adder subtractor module. In this module, we input two numbers and give the result as a sum. The reason why I call this adder subtractor module, if you add two numbers with same sign, which is positive, positive, and negative, negative, I call that addition. And when you put different valued numbers, let's say one positive and one negative, then it gives the result accordingly. If the positive one is greater, it gives a positive result. If the negative one is greater in absolute value, then it gives a negative one. So it's basically an adder and subtractor. Our second module is a multiplier module. In multiplier module, again, you input two numbers and have the multiplication as a result. In this multiplication, since we multiply two 15-bit numbers, you can see here, we actually obtain a result of 30 bits. However, in order to stay within my conventions, I take the output as from the 19th index to 5th index, and that's the result. Our third module is a divider module. You can input any number you want. You can also calculate fractions with this divider module. Again, you input two numbers and have the output result in this module. You can make mixed sign divisions, and also you can obtain irrational numbers as well. The final module is the integrator module. Integrator module itself has four functions. First, you can integrate a second-degree polynomial from any boundaries. The other is cosine, sine, and the natural exponential function e to the power x. By using function type input here, you can choose between these modules and you can give the corresponding coefficients of the numbers. Like, for example, number one is the coefficients of x squared, number two is x, and number three is x to the power 0, which is a constant. And you can also define boundaries. Our final module is the VGA module. In VGA module, it's basically the module that makes us available to show our results on the screen. The timing parameters of this VGA module is for 480 to 640 resolution. And it gives a result in binary. You can see the whole code in here. This defines the output metrics of the final result. It's an algorithm. And that's it. Moving on to the basis tree instructions, I built it in a user-friendly way. The buttons are used to load numbers that you're given. These 16 switches here are for the numbers. The most left one is for the sign of it. When it's 0, it's positive, and when it's 1, it's negative. The rightmost fifth ones, these 5, are for the decimal point. So we have a fixed point between these two. And this part is for the integer value of the number. The left button is in order to load number 1. The middle one is number 2, and the right one is number 3. The lower one is for the lower boundary of the integral, and the upper one is for the upper boundary of the integral. When you press left and rightmost, then you input the mod type. Mod type selects between the modules of adder, subtractor, multiplier, divider, and integral. You can see the mod type here in the leftmost LEDs. These two LEDs indicate the mod type. And you load the function type of the integral, which is like polynomial, sine, cosine, and e to the power x, by pressing these two lower and upper buttons. And you can see the function type via these two LEDs, the rightmost ones. Moving on, we have the VGA screen. Again, as I said, it will give the results in binary, and it gives the results in my convention. So we have a fixed point right between there. These 5 are the decimal ones. These 10 are the integer one, and this is the sign of the number. Right now, it's all 0 because no input is given. So Starting with addition and subtraction. First, I assign all numbers 0. And I choose the mod type 0, 0, which is adder subtractor. For instance, let's say I want to add 1 and 2. I input 1 first, 1, 2, 3, 4, 5. This is 1. And then I input 2, and it adds up and show me as 3, as indicated over here. You can also make subtraction. For example, if I input -3 and 2, I get the result -1 as expected. Moving on with multiplication, I choose the mod type by these two switches. Multiplication is 0, 1. So I load multiplication model. You can see from the LED here that we are now in multiplication. Let's say I want to multiply 2 with 3 and get the result 6. 2, 3, 4, 5. This is 3 and this is 2, and I get the result 6 as expected. You can also multiply one positive and one negative number. Let's do the same thing with -1 and 3, let's say. Then I get -3 as expected here. And when you multiply two negative numbers, of course, you get a positive result. Let's multiply -1 with -2. Then I get the result 2 as expected. Moving on with the division module. Division module is 1, 0, so I load in the division module. This indicates that we are now in the division module. And let's say I want to obtain 1 over 3, which is actually a fractal that's infinite. So since I am using 5 decimals after the fixed point, it will give the result as 0.33333 because that's my approximation. So if I divide 1 with 3, you see this number. If you calculate it, this is 2 to the power -4 and this is 2 to the power -2. So if you sum them up, you will have the result 0.33333 after, so basically 5 threes after the fixed point, which is what we expect. Moving on with the integration module. Integration module is set by 1, 1. So I load 1, 1. Now these two LEDs indicate that we are in the integration module. And moving on with the polynomial integration, this is the function type 0, 0. So I input the function 0, 0. These two LEDs are 0, 0. So we are now in the integrator module, polynomial function. So if we integrate 0 to 1, x squared plus x plus 1 dx, we will obtain this number, which is 11 over 6, which is the correct result, and this corresponds to 1.83333. And if you calculate this number, you will see exactly that's that. Moving on with the sine. Sine is again in the integral module, but this time the function type is 0, 1. So I set the function as 0, 1. This let shows me that I am in sine right now. And if I integrate 0 to 1 sine x dx, I get this result. This result is 0.46375. However, the actual result, if we calculate by hand, is 0.459 and etc. There is a 0.009-ish error between my result and the actual result. That's because since sine is a continuous function and this computer system is a discrete system, I can only use approximations of sine, and in my project I took the Taylor series expansion of sine function and took the first 4 terms, and that's the result of this error margin. With more terms added from the Taylor series expansion, this error can be minimized, but then the computational work will be higher. Moving on with the cosine, it's 1, 0. I load cosine function. This LED indicates that now I am in cosine. And again, integrating 0 to 1 cosine dx, I get this value. This value is 0.84 and 0.843625-ish. That's also very close to the real value. The real value is around 0.8141-ish. Again, the error occurs because of my approximation of the cosine. I again took the Taylor series expansion and took the first four terms. With more terms as chosen, this error margin can be narrowed down. And lastly, moving on to the e to the power x, I take the function type as 1, 1 and load it. This let indicates that now I am into the e to the power x, and then I integrate it from 0 to 1 e to the power x and get this result. This result is 0.65-ish, where the real result is 0.718. Again, the error is from the Taylor series expansion. I also used e to the power x's Taylor series approximation for my calculations and took the first four terms again. And the error is result of that. If I had chosen, for example, 6 terms, then the error would be lower. So that's it. That's my whole project. Thank you for listening.